Hello, everybody, and welcome to another wonderful day of physical chemistry. So, over the last two lectures, we built up the idea of how we can form a Hamiltonian for a hydrogenic atom. And by doing so, we were able to separate it into an angular and radial component. So, this leaves us with a nice radial Hamiltonian function. So, again, this radial Hamiltonian features a portion due to the kinetic energy in the radial direction, the angular direction, and then again an attractive potential which favors electrons being close to the nuclei. So this is a good set of a good Hamiltonian. However, if you remember, the real reason we love a good Hamiltonian is it helps us generate a set of eigenfunctions. So now we need to figure out what are going to be some potential eigenfunctions for this new Hamiltonian. So one of the things that we're going to, you may first notice, is that these first two terms are going to be pretty much invariant depending upon the angular momentum. But unfortunately, our Hamiltonian does actually change upon the choice of total angular momentum of the system. So this angular dependence upon the angular momentum is really going to change the form of the radial eigenfunction upon the choice of L. And one good way to look at this is under some extreme circumstances. So if L is essentially anything but zero, what we're going to notice here is a positive potential. And so what this has is the net effect of if I have a lot of angular momentum, this means I have an electron kind of circling the nuclei. And this kind of generates the same sort of centrifugal force that you'd expect by what happens when I put kids on a merry-go-round. Faster the merry-go-round spins, the more towards the edge they go. And this is exactly what we tend to see under high angular momentum conditions. And not too surprisingly, this angular momentum is going to be most felt at very short distances. Because at very short distances, this 1 over r squared term is really going to dominate the whole expression, as it will quickly become an infinitely positive or repulsive potential. However, if L goes to 0, then what we're going to find, the major term we're going to find dominating is this attractive potential term, which is going to give me very negative or attractive potentials at at short r's or low r values. And as such, we're going to kind of see two varying functions of our radial distribution. So in general, what we're going to find is no matter the function, because at long distances, this negative potential with its longer range 1 over r dependency is going to dominate. If we go far enough out, we're going to see essentially this asymptotic die-off of the potential. Further out we go, less and less likely I will be to see the electron out there. And as a consequence, we're going to see again the energy, the potential energy essentially die off and eventually level out to 0 as this term becomes less and less relevant. But consequently, so will the probability density. They'll tend to find a very low probability density out here as well. However, once I get close to the nuclei, we enter these two regimes. So if L equals 0, I've got no centrifugal repulsion. I'm going to be very likely to find an electron hanging out close to the nuclei because it's got nowhere to go. But as soon as it needs to start moving, it only is going to incidentally pass by the nuclei. And as the angular momentum becomes larger, I'm going to become much less likely to find the electron near the nuclei. And it will be pushed out further into kind of these intermediate ranges. And as a consequence, what we're going to find is a general form of a radial distribution at short ranges, we're going to be dominated by this, again, radial term, where I'll have larger probability densities further out as L gets larger. As soon as I have, However, if L is 0, then it's actually going to be possible to have uh, a a radial wave function at the nuclei when r is equal to 0. However, as L gets larger, we're going to note that at very small distances, our wave function is still going to be very close to 0. So this term is really going to tend to dominate under small r's. However, for large r's, exponentials always win. And no matter what our angular momentum, we're typically going to have an exponential die-off. So these two behaviors kind of make sense. However, in order to get our radial wave function right, we also have to knit these two behaviors together. And to do this, we essentially make use of a polynomial term, which we give the value of L. Variable of L. And so this essentially is going to knit together this kind of more repulsive force and this exponential die-off. So for small values of R, this polynomial term is going to be dominated by a constant. And our general radial wave function is going to be approximately equivalent to just this R to the L function. So again, this means if L is 0, we have a wave function that has a constant value, roughly 1, essentially just dampened down by these two additional terms. However, as soon as we introduce a larger angular momentum, it's going to essentially push the system away, as at short distances r is close to 0, and so will the wave function. However, as the values of r gets larger, what we're going to find is that our polynomial term will take on the general form of our radial function times our n. So this is going to be a integer value. It's more or less going to be our principal quantum number, just like it was for particle in a box, minus the angular momentum minus 1. However, because our first term is r to the L, that's going to cancel out this minus L component. So our general radial wave function will take the form as r to the number to the principal quantum number minus 1 times essentially this exponential decay term. So this is going to show that while all expressions are going to have an exponential decay, the rate of this exponential decay is going to more or less be dictated by the principal quantum number here. So this n. With a larger n value, essentially giving us a larger probability at these longer distances. Small values of n is going to give us very small numbers. And generally, n is going to be given by an integer, which has to at least be 0, which has to at least be the value of L. Because again, n minus 1 has to be a real number, but so does n minus L minus 1. So no matter our choice of n, it has to be greater than L plus 1. And again, as a reminder, L has to be greater than 0. So when we go ahead and set up this expression, this is going to give us a general wave function of a normalization constant times our polynomial term times this exponential decay. But you'll notice that instead of having a value of r, we have a value of rho. Now, rho here is essentially a way of trying to embed constants. So rho is going to be a function of, indeed, our radius. So again, we do see this radius to the angular momentum, a polynomial expression as a function of radii, and an exponential decay with respect to radii. But it also has a dependence upon the choice of nuclei, where z is going to be the charge of the nuclei, n is that integer value that we previously demonstrated, and then this little pesky variable of a. So a is going to essentially be a function of A naught, which is also known as the Bohr radii. It more or less is based on a series of empirical constants and has a value of about 52.9 picometers, or about 0.0529 angstroms. Um, and what happens is we're going to have this Bohr radii essentially modified by the difference of the ratio of the mass of the electron to the reduced mass for the system. So it is worth noting that this ratio will generally should be fairly equivalent to 1, as the reduced mass of the system for essentially a fairly large system should be roughly equal to the mass of the electron, since the mass of the nuclei should be much greater than the mass of the electron surrounding it. So we often essentially truncate this A variable as simply the Bohr radii. Now, this general radial wave function will actually have a dependence upon our choice of n and upon the choice of angular momentum. So the lowest value of n with no angular momentum, we're going to tend to see just a fairly nice exponential die-off function, no increased radial term, and the polynomial essentially is a constant. This, however, puts more of the brunt of the function upon the normalization constant. However, as we increase the number of n, what we're essentially doing is increasing the number of radial nodes, because again, this makes sense. I increase to the next energy level of wave functions, and I should introduce an additional node. And we see this as we go from n equals 1 to n equals 3, where I just keep increasing the form of my polynomial. However, this is all assuming I have no angular momentum. So let's see what happens if I take my n equals 2, L equals 1, and instead I increase the angular momentum. And now what we note is that we don't actually see the generation of any radial nodes. Instead, I have this pesky function of rho. Now, what this is essentially denoting is I'm not generating any additional nodes in terms of radial nodes. Instead, if you remember your spherical harmonics, I've generated an angular node. And part of this angular node is a zero probability of finding the electron, again, at that core, because the angular node should cut through the center of the atom. And then again, I have a nice even die-off. And we'll see the same thing with the n equals 3, L equals 2, where again, I have no angular radial nodes because I have 2 nodes, but they're all radial. They're all angular. And this is indeed what we're going to find with n. N is going to give me the number of nodes present in the system. However, it's going to be both in terms of angular and radial components. However, L gives me the number of angular nodes. So if I have an n of 1, I have no nodes. N of 2, I have 1 nodes. It can either be radial or angular. N of 3, I've got 2 nodes. Both of them could be radial. One of them could be radial and one could be angular, or both of them could be angular. Now we can take these set of functions and look at our radial distributions a little bit more kind of precisely or graphically. Now, again, one of the things I want to make note of is our cases when L equals 0. So n equals 1, L equals 0, I have this nice exponential decay. Now, when n equals 2, L equals 1, again, no angular motion, I'm still going to have a fairly high probability of my system being found near the nuclei. Single crossing my wave function will cross 0 once, which again makes sense because this will be a single node, and I'll have an exponential die-off of my wave function at long ranges. Now, if I was going to turn this into probability densities, this would be positive probability densities here and here, with again a slow die-off of the probability density. As n goes to 3, L is still equal to 0, and indeed, I continue to see I essentially just add another node. But again, I always, in each of these cases, will see a probability density, a positive non-zero probability density at the nuclei. However, let's go ahead and take a look at this n equals 2 case. So if I introduce this angular motion, I spin the system up. I'm generating essentially an angular node as the system moves. But as a consequence, I've essentially pushed all of the probability density away from the center of the nuclei. And so I just have one simple peak of the density go up and then an exponential die-off. And one of the cool things to make note of is that as I push the system away from the very center, I actually have my peak probability density a little bit closer to the nuclei than I will from the simple L equals 0 case. So again, this is actually a cool feature, and you may be able to start to see the buildup of the atomic orbitals, which we're going to start talking about more explicitly next time. However, in the meantime, I kind of want to take a moment to really focus in on some of the meaning of those values of n. So it turns out that we can apply our Hamiltonian to these wave functions, and we generate a fairly general set of eigenvalues. Now, one of the cool factors I want to show is that indeed our eigenvalues pop out a whole bunch of constants, which isn't too surprising considering how complex those functions are. But it turns out it only has dependence upon two variables. The first makes fairly logical sense. It's the charge of the nuclei. And this is partially going to be because the charge of the nuclei is really going to show us the depth of the well. But second component is going to be this n value. So this n integer value is going to be dictating our energy levels. It's worth noting that while all these constants are going to actually pop down to giving us a single energy value, about 13.6 eV, or about 2 times 10 to the negative 18th joules, what we're going to find is that our energy values really is going to primarily be dependent upon n. So n is really going to be our shorthand for talking about energy levels. And as such, it's typically referred to as our primary quantum number. This is going to be more or less, for a hydrogenic atom, the only thing that dictates the energy of the system. This should hopefully make a bit of sense as if we look back to our hydrogenic atom, or our particle in a box, our harmonic oscillator, even our rigid rotor. As we typically found, what was the only major control on energy was more or less the number of nodes. Because the more number of nodes I had, the faster I need to move. And this is really what we're seeing here. The only dictation upon the energy is essentially how fast I have to jump past the node, no matter what direction that those nodes are pointed at. And indeed, this is exactly what we see. The energy has no dependency on our value of L or m sub L. So it doesn't actually really so much depend upon the shape or where those nodes are pointed, just simply how many nodes. And this is actually a fairly cool feature. So now with kind of these radial distributions in hand, and as a general idea, we're going to be knitting them back together with our angular distributions over the course of the next several lectures to really build up our hydrogenic set of orbitals. So we can actually finally take a good look at the hydrogen atom. Till then, take care.